Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be taking a little bit of a jaunt down the road of physics as we talk about the origins of quantum mechanics, with specific focus on two key experiments that really helped establish the quantum nature of the world. And one of them was actually what Albert Einstein won his Nobel Prize for, despite the fact you may have never heard of the experiment. So the first of these phenomena was a classic stumbling block for early 1900s physicist, and it's blackbody radiation. So you may not be familiar with the name, but you're probably familiar with the phenomena. The idea is that if an object is sufficiently heated, it will produce a wide range of light. So this is the reason why, as you heat up metal, it will slowly turn red. And as we've seen previously, red is the lowest wavelength, the longest wavelength of visible light. And if you heat it up even further, you can start producing other spectra all the way up into white and even blue light. And this is actually how incandescent light bulbs work, where you take a tungsten filament and you heat it up to 4,000 degrees Kelvin. Wowzers, that's actually what we were hitting. Also, one of the reasons why incandescent light bulbs are generally not that efficient. Go halogens. And of course, we have the largest black body emitter in the solar system, the sun. And one of the reasons why the sun glows is because it is just so hot that it starts emitting photons. And the basic idea behind black body radiation is that as an object heats up, we have all these small little molecules and atoms that will start moving back and forth. And these atoms move back and forth and they change speed. Every change of speed can be related to a release of photon. So the hotter the objects, the higher energy the photons released. But also, the hotter the object, the more photons that can be released. So you heat an object up sufficiently, it will release a lot of photons of very high energy. And one of the cool ideas that Max Planck established was the idea that as the frequency increased, so did the energy. And this is one of the reasons why we say low wavelength, high frequency light tends to be high energy. And he related these two phenomena with a constant, which we now call the Planck's constant, which is about 6.6 times 10 to the negative 34th joule seconds. So yeah, it's a little bit of an odd number. But one of the key things is that he found that this energy relation was based on some sort of integer value multiplying the frequency of light times the energy. And what we now know looking back is that this n factor is going to be the number of photons released. So if I release a lot of photons at high frequency, I'm going to have a lot of light produced. However, while this experiment essentially suggested the existence of photons, it didn't definitively prove it. And one of the reasons why photons are so important is because this is the idea that light can come in discrete packets. To do that, we had to go to another common conceptual stumbling block around 1906, when Einstein published his paper on the photoelectric effect. So the idea of the photoelectric effect is I go ahead and I shine light on a metal sheet. And this light will then emit an electron. And we can measure the energy of the light coming in based on our equation from blackbody radiation. And we can go ahead and measure the energy of the electron coming out with more traditional physics, where the energy of a moving object can be given by 1/2 its mass, so in this case, the mass of the electron, times here, because we already have too many v's about, we're representing velocity as nu. And what they generally found is that it turns out that you need to have, in order to have an electron emitted, the frequency has to be above some given threshold. Below which, doesn't matter how much light you shine on the metal sheet, no electrons are emitted. But after we hit this threshold frequency, then as the frequency increases, we're going to have the ejected electron having increasing energy. And this should make sense. The more energy I put in, the more energy that electron's going to come shooting out with. But again, similar to what they also found is that as I increased essentially the intensity of the light, I would increase the amount of you could end up producing increasing the amount of current. So essentially the amount of electrons being shot out, but only once you got past a certain threshold frequency. And the only way to actually explain this is if you have to have a certain amount of baseline energy coming in with this photon to eject an electron. Having 2 or 3 photons that add up to this energy isn't sufficient. And the only way this comes about is that if, just like we know the electron occurs as a discrete particle, it also has to occur that the photon is a discrete particle. So 1 photon in, 1 electron out. And then we can use the energy of that individual photon and that energy of that individual electron. And again, this only will occur if that incoming photon energy is greater than the energy binding the electron to that metal surface. We call that energy the work function, or the electronic work function, or occasionally, because we're working with metal surfaces, the metal work function. This work function will be an energy typically reported in EV, or electron volts, of how much energy it takes for the metal to release that electron. And again, as once we exceed that work function, as the frequency of the incoming light increases, then all of that remaining energy will go into the ejected electron. And again, if the intensity of the light increases, or the number of photons coming increases, so will the number of electrons, but not the energy of the individual ejected electrons. So we can go ahead and use this basic concept to build up a mathematical relationship. And this is more or less the idea of energy in equals energy out. So the energy coming in is all going to be based on how much energy my photon has. Then that energy has to go into 2 places. First, we have to overcome the amount of energy binding the electron to the metallic surface, and then the rest can go into movement, so the kinetic energy of the electron. Well, we can measure the energy of an individual electron just using Planck's constant times the frequency of light. The work function is going to be based on the identity of the metal, and we have the mass of the electron and the velocity of the electron. We know the mass of an electron from the earlier Mulliken oil drop experiment. And so if you measure the velocity of the electron and you know the frequency of the light, you can determine the work function. If you know the work function and the frequency of the light you shot out, you can figure out how fast the ejected electron will be moving. And this actually allows quite an efficient description of the movement of electrons and how they interact with light. So what we're going to be doing next time is taking the same basic idea, but applying it to atoms, because I can shoot light at an atom and make the electron move. Similarly, movements of electrons can generate light. So next time to finally dive back in to the middle of an atom. Till then, take care.